This is the outline of my talk. I will talk first about electrochemical energetics and kinetics from a ground canonical constant potential viewpoint, so some theoretical and computational results. And what I kind of want to transmit is a bit my idea about how to think, describe, and compute without ambiguities, which is a bit a problem in electrochemistry, that we deal a lot with ambiguous quantities and words where the meaning is not fully clear, at least in my opinion. And I think Axel had already a discussion about certain quantities, gave some examples. In the second part, I want to talk about the capacitance of platinum-111. It's a very interesting problem, and there's also a poster outside by Lang Li. She's here in the long-term workshop, and that's basically her work that I want to talk about there. In the end, I want to talk about our machine-learned potential that we recently developed that can do, in some sense, electrochemical simulations. Now, the central aspect I want to talk about is the potential dependence. So this is what I've been interested in, I think, the last probably 8 years, thinking how does potential dependence arise, how we can implement it in a simulation, and what does it mean? And so how can we, so first I should maybe say, as Axel says, what is the potential? And to me it's totally clear, there's only one answer to this. The potential is what we measure outside, this electrochemical cell. So the potential is really what the experiment does. And so we measure here differences between electrochemical potentials, and that's everything we need to know about the electrode potential, in my opinion. Or this should be the only thing we need to know to describe or build up a system of consistent energetics in this problem, because we don't just know these electrostatic problems inside the solution. We don't know much about them. It's not just that we don't know much about them, it's also not very clear what it means. Like if you look into the classical electrochemistry literature, there's certainly a lot of discussion about the importance of electrostatics, inner potential, outer potential, surface potentials. But it's not really clear what that exactly means. I mean, I've drawn here some effective possible electrostatic potentials in my plot. But I believe they are not really well defined, or a bit some kind of ambiguous quantities. And to underline what I mean, I want to go back to a very old paper. This is by Guggenheim from 1929, and this is literally the paper that defines the electrochemical potential. So I want to just read this to you. Here it says, the function mu tilde should be called the electrochemical potential, and it has a real physical significance. The conception of splitting the electrochemical potential into the sum of a chemical term mu and an electrical term has no physical significance. For one can assign an arbitrary value to phi for some point in each medium, and this will, for the ion of each type I, determine mu. This is totally kind of clear to me. If you think about it long enough, it's totally clear. And to every, I think, Ab-Initio person, DFT guy, it should be clear, because we always kind of just renormalize or set an average potential to 0. Now, how does this work then end? I mean, there's a lot of discussion of what we mean by this electrostatic term here, but in the end, this is literally the last sentence of this publication that defines the electrochemical potential. It says, it is therefore probably best to restrict the expression electric potential to mean the electrostatic potential of electrostatics, and to avoid its use in the description of physical phenomena involving ions and electrons. And so this, I think, says it a bit all about the electrochemical.
Yeah, make him a rock. Why doesn't then he call it just chemical potential?
No, he says basically the problem is if you go between different media. That's the problem. Yeah, where you can have, or if you have, so if you have one medium and you have, like, he doesn't, let's say a drift diffusion equation is not what he says is a problem, but he says a problem is as soon as we go through different media or try to compare energetics in different media. So this is the problem, and this is the problem of electrochemistry, because we do things in the contact, or we try to understand energy differences by moving things between different media, right? And talking about ions and electrons.
Yeah, but chemical potential are always in the medium, no matter. I mean there's nothing special about electrochemistry. I mentioned
yesterday, I believe one could all do everything with chemical potentials. So if you have a total energy calculator that gives you energies, or let's say also for ions, and everything correct, then we can all stop talking about electrochemical potential and just talk about chemical potential.
Isn't it at the very end all about with respect to what you measure what?
Exactly. This is the important thing. No, that's the important thing. So it's about measure what to what, and we can only measure, or the real thing that we measure is energies, relative energies, right? Not relative electrostatic potentials. This is not what we measure.
As well, you can measure with respect to the bulk of the if you measure, for instance, with respect to the bulk of the metal, then the chemical potential is the distance of the Fermi level with respect to that point. If you measure with respect to the point in front of the solution, in front of the metal, then you have one thing, bulk potential. Yeah, all of it. Yeah.
Okay, maybe. Can I explain one thing? Look at experimental electrochemistry, right? There you define the proton electrochemical potential to be 0. That's a reference energy. The hydrogen gas is a reference energy, and the SHE is defined 0 then, because you define the SHE via the proton electrochemical potential. So there's nowhere is there outer potential vacuum level, there's nothing. I mean, electrochemistry in water works without knowing anything about vacuum. It works just because you define references. I have actually a slide to this. I mean, it's all about, now I'm going.
Yeah, perhaps you can
I will not finish this off.
interrupt your
All right. No, it's really just about reference energies. So the problem is this. Yeah. Sorry. Now I'm getting excited, because I have no. The problem is very simple. You know, chemistry works. I mean, in order to build up any kind of consistent referencing scheme or energetic model or kinetic model, we need consistent references for the energies and free energies, and this is working in chemistry with the periodic table. Yeah. Oh, pardon. But in electrochemistry, this doesn't suffice, right? Because we deal with charged species. So we need to, like, for example, what is the ionization potential? Well, what is the free energy change for ionizing something? Well, you need to tell me where do I put the electron. That's the important thing. So there suddenly when you deal with stability of charged species, you need to tell me you could call this electrostatics, but it's more like where does the electron go? Where's the electron electrochemical potential? But as I said, experimentally nobody talks about electrons. I mean, you don't need that. You define this, right? So I'm deeply convinced you can, if you have a total energy calculator without electrons, but that does everything correct, you don't need electrons. I mean, you don't need to know about electrons. But this is my opinion on this. Oh God, don't finish my thought.
Maybe this is something for the afternoon discussion or
Yeah.
as you already
Actually, there will be this time for discussion this afternoon.
Yes, that's what I mean.
Yeah.
So
No,
that's,
but also there's going to be plenty because one of the speakers is there, so cannot make.
Okay.
So we'll have this discussion.
I think it would be super nice if we discuss in the afternoon. But
Just continue with your
I will talk.
presentation.
Let's say, forget everything I said. What I said. Forget everything I said without electrons, because I will do with electrons. Okay, like you, like all Ab-Initio persons, I will do with electrons because it's the natural choice, right? If you do Ab-Initio calculation, you have access to the electron electrochemical potential, and so it's also kind of natural to bias such a system by kind of coupling this system to an electron bath, right? Exchange electrons with some reference electrode, as you said, to bias this system. Now, can you bias the system in periodic boundary conditions? Well, you cannot really, because you have a problem of charge neutrality in this extended system. So what you really would have to do in principle is to exchange another charged species in this system to keep electron neutrality. This is what nature does, right? Building up of a double layer, as Axel said, to keep everything charge neutral. Yesterday we heard, well, doing this ground canonically, these ion, let's say, insertion moves for the double layer, this is like problematic, yeah, in a condensed matter system. So we can't really do this. I don't do this, and most people don't do this. We have some tricks. My trick, or my favorite, well, the trick that I have been using for a long time is building these joint models, let's say density functional theory, coupled to a continuum solvent model, and there were discussions by Richard here, I think in the earlier talks. Yeah, not much to be said, only that the important part here, I think, is the electrolyte model, so the countercharges in this solvent model that allow you now to keep charge neutrality in the simulation box, even if you exchange electrons and apply a potential. And so in this type of setup, you can now do constant potential simulations. Now, is this the only way? And I'm also thankful for Mira, she already said it. It's not the only way. In fact, in the literature, people have talked about many different ways to bias these systems or to apply effectively a bias to these systems, to these interfaces. And there's obviously the constant potential, let's say, situation, which is in some sense, in my opinion, the real thing. This is consistent to experiments, but there are also these ideas that you can maybe do at constant field or constant charge. This down here, constant charge, is of course let's say the easiest way in some sense, the most natural way for a DFT calculation where you work in the canonical ensemble. But to be honest, if you do these simulations and you really look what happens and what you do, it feels, and it feels very different. So constant potential means variable charge. Yeah, you put a potential, you observe a charge. Constant charge is you put a charge, you observe a potential. So this feels very different, and it is kind of also very different.
So, Nico, just because you said something like consistent with the experiments, that would apply of constant potential. That applies only if you would really simulate in a macroscopic system.
Sure.
Not really, it's not consistent if you go then to a typical supercell or our microscopic system. So therefore I feel a bit uncomfortable with
true.
the statement.
True.
This is consistent with experiment.
We make a lot of approximations. What I'm saying is like if this, let's say if this continuum model would be the truth, if this would be without fault, then this would be the true system. Huh?
If this is really
for thermodynamics, let's say.
If you have the full double layer in your cell, we agree.
Yeah.
If this is not the case, it's probably quite often.
Absolutely. No, I totally agree. If I'm always thinking of the ideal case that we can do these simulations. Yeah. Exactly. Okay, so just here a note, if you do simulations in these ensembles, you really do different things, and you compute or talk about different energies. So in the ground canonical ensemble, I'm using here these calligraphic symbols, and for the canonical ensemble or constant charge simulations, just the kind of conventional symbols. I'm avoiding the omega because the ground canonical ensemble, nominally I think it's only really clear for a single component system or defined, but it's at constant volume, and really the experiments here are at constant pressure. So it's a bit not clear to me why I should call these simulations somehow omega, and so I will just call them always calligraphic, same symbol, but calligraphic as the canonical case to just say that there's a Legendre transform going on in between here. Yeah? Okay, so we do really different things. It feels different. And actually in simulations, it is very different, the outcome. So this is an example. This is just a sketch, but people who do these simulations know that this is happening. So if you simulate, for example, a minimum energy path for an adiabatic proton adsorption reaction, the DFT in natural elastic band, you get a constant potential result that looks like this, and a constant charge result that looks like this, and a constant potential result that looks different. So this is just proton adsorbs onto the surface. And also what you simulate is completely different. Here, for example, there's nowhere an electron exchange from the external bath happening along this red path. Along the green path, there's really here when the proton adsorbs, there's suddenly an electron coming in from the external circuit. So it's very different what we do. Somehow, empirically, if you make infinite cell size some things, let's say, then it looks like, oh, this is kind of the same. But I was always, since years, very frustrated that I felt this looks very different. It looks just intellectually so different. Is it really okay to do this constant charge way as I describe it, or should I really go always constant potential? So in the last 2 years, I think we made some progress, or we or some collaborators, because we realized what we actually fundamentally have to understand is how to transform between ground canonical, let's say, potential energy surfaces and canonical constant charge potential energy surfaces, or rather, what's really interesting is like how do stationary points transform, right? Because these are the points that are interesting. So the local minima or transition states, or this is probably the relevant quantities. We should be able, maybe, hopefully, to say something about the stationary points in these ensembles. And indeed, it was a bit mathematical kind of tour de force, maybe not tour de force, but it is a bit like tedious to do, so that's why we have it only on archive, because it's a bit too many formulas. But what you can show the first thing you have to show is how the forces transform, and you can show that ground canonical forces are canonical forces, so that means that stationary points, so points where forces vanish, are accessible in both ensembles, identically accessible in both ensembles. That's great. If we look at the Hessians, however, there's a small problem. So the ground canonical Hessian is not identical to the canonical Hessian. There's this correction factor. And so it means there's potentially a problem in finite cell size, but luckily in infinite cell size, this correction term goes away. So in infinite cell size, we have identical Hessians. And so in infinite cell size, things are fine. Yeah, stationary points are identical, so we can, in principle, find all the information also in the canonical potential energy surface.
Can I ask a quick clarification?
Yeah.
You talked about those landscapes.
Yeah.
You're talking about forces. Can you tell us what you do? How do you define the force?
Oh, okay. Yeah, I have, of course.
Right on the board.
Yeah, I just tell you, it's just a derivative.
Of what?
The derivative of the ground canonical energy and the derivative with respect to positions, and the derivative at constant position and at constant electron electrochemical potential. And then for the canonical case, just the same thing, derivative of energy with respect to positions at constant number of electrons and at constant...
So it's not the definition Newton would have written out or anybody else since. It's
no,
the derivative of the energy.
No, it is
energy.
It is
not,
the energy
not
of the...
grand canonical, energy with respect to position.
Yeah, the energy, but the energy is a function of charge or of potential, right? So it's just the energy derivative at something constant. Yeah.
It's the energy, not the grand canonical, not the Gibbs free energy. It's the energy.
No, it's the energy. Sorry, the energy.
That's okay.
The energy.
But then it doesn't matter on the ensemble, of course, right? Because the energy is always the same in every ensemble.
Well, the Hessians are not the same. No, because
what?
No. Because you do a Legendre transform. I mean, this
Hessians of what? The
Hessian of this.
If it's the Hessian of the energy, it's always the same.
Okay.
It's the Hessian of the Gibbs free energy, of course. That's another
question. It's the Hessian of the ground potential, the ground canonical Hessian.
But the force is the derivative of the energy or of the grand potential.
Okay, let me again. Let's see where's all the math.
That matters, right? Or are we saying something similar?
Okay, so this. Okay, it's this. Yeah.
Okay.
Is it clear?
I think
Is that clear?
The right equations are E.
This is standard.
The energy.
This is standard.
That's what Newton would have written down in Hessian.
Yeah. And this is what we do. Yeah. This is what we have to look. What we do.
These are the same. These forces.
Forces are the same. At corresponding configurations.
That doesn't make any sense.
At corresponding configurations.
No, that doesn't make any sense because I can integrate the forces and get my energy landscape. That means your cursive F and your other F are the same thing. That doesn't make any sense.
Hessians are different. No, this is also shown. We are not the only ones. This is really simple math.
Then cursive F and F are identical functions except for a constant.
Look,
but that's just math, right?
The Hessians are different, and it's like you can do the numerical calculation. People have done this. People know this. This is not unknown. People know that they are. People know that Hessians are.
I have a function which is identical first and second derivative. It's the same function except for a constant.
No, you have to pull through derivatives through the Legendre transform. That's very difficult. It's very difficult. Yeah, look at this. So you have to compare, of course, corresponding.
But it wouldn't be that this is only true in the stationary points.
This is no. This is general. This has nothing to do with stationary points.
The constraints are different.
So the math is here. Okay, the math is here, and we can go through this. And
if I have a function which has identical derivatives, every on space, and I integrate it, then you can only divide by constant.
Derivatives are.
You have to pull this through. This is the important thing.
There are some manifolds which are different.
We look at corresponding configurations. Of course, we can't just compare nonsense, right? We need to compare nominally identical states. Nominally identical is
I see what you're doing.
A charge configuration which has a certain work function or potential, and so and here are these dependencies. So you need to pull derivatives through.
Okay. I'll follow. Thank you.
Okay. I'm happy that people are interested because it is really interesting.
I forgot the subscript. I see it.
Okay. Yeah.
Clarification. So, what is dimensionality about? This R is 2D or is a proportional number of particles?
This is whatever. Like this is 3n. This is 3n dimensional.
So it's a proportional number of particles.
It's proportional to number of particles, and then in 3 dimensions. Yeah, 3n. Exactly. Okay. So, but you agree that if this holds, if this is true what I say, then okay, there's no problem. We can recreate stationary points. We can identify stationary points, identical stationary points in the infinite cell size limit. That is kind of important at the baseline to at all be sure that the constant constant charge ensemble can do potentially the same or what we want. Now that we see that somehow stationary points are accessible, you can also think of a method to reconstruct, let's say, the ground canonical information from the canonical information. We did this here, and I will talk about this in 1 second. Last, I want to say, is this done in the typical simulations? No, it's actually not. The typical simulations, they take energy differences in the canonical ensemble and then do some let's say, transformation that's not a Legendre transform. They just substitute n of mu basically here. And then they claim that this thing is the energy in the ground canonical ensemble, the energy difference, sorry. And really this is not the same. Only in the infinite cell size limit this is the same, but it's very hard to understand. And so the math is here and just what supports that this is really correct. Just one day after we put this on archive, Georg Kastlunge, he calls us and said we're just working on the same thing. And he put 5 days later, he put out an alternative mathematical proof, but proof that proves basically the same thing. So this is really support that this makes sense what we're saying here. Okay, so infinite cell size limit is fine, but only when we compare energies between systems that have differential changes. So let's say one adsorbate in the infinite cell size is different, or a geometry of one thing is different. This is incorrect, so let's say differences are totally wrong in the canonical ensemble if you look at, for example, the stability of a surface that's covered with a full layer of hydrogen relative to the energy of a clean surface. If you do here the canonical energy difference, that is not the same as in the ground canonical ensemble. Because you have still always a work function difference, right? That's the point. You cannot, this is not evaluated at the same potential. Okay. Good. Now I feel I need to go back to, and I will not finish this talk, but that's okay. Yeah, so I said somehow stationary points are accessible. There should be a method to get rid of this problem, right? And the method is really trivial. We published it here in this publication. What you have to do, you have to somehow recover the information contained in the ground canonical simulation. So what you have to do is you simulate multiple charges, and then you can, of course, reconstruct a, let's say, universal underlying truth from Legendre transforming these canonical individual, let's say, pointwise, Legendre transforming this canonical potential energy surface in some sense pointwise. So you see this then here, this is this ground canonical potential energy surface for an adsorption pathway. Proton reacts to surface, to a hydrogen on surface, and you have the electrode potential and reaction path. And you can see the energy here, and you can see that the constant potential simulation, natural elastic band, accesses this landscape or like probes this landscape kind of at constant potential conditions, while the constant charge curve, and that's why it's different, probes this landscape along kind of curved lines. Yeah? So you're not allowed to compare this energy with this energy directly. But if you don't do the direct comparison in the canonical ensemble, but do first the transformation to reconstruct ground canonical, of course you can evaluate the ground canonical. And you can see this better maybe here if we plot now only the energy of these stationary states, transition state, final state, initial state as a function of electrode potential for potentiostarted and Legendre transformed canonical simulations, you can see that the diamonds, this is information from these constant potential naps, they align on the potential, and the standard canonical naps that you Legendre transform, they don't align, but you still recover same information, right? You have here point, point, point. So it all recovers or provides information on one underlying ground truth. And so this is now the way that you can actually do canonical simulations but recover all properties, or for this case, of the ground canonical system. Okay. Now, let's go approximate. This was more or less not approximate. Now we go a bit approximate because we want to learn something. And so the point is, aren't these just parabolas? And I would say this looks very parabolic. So we can actually build a capacitor model, and you write it like this. Energy, and here's a very important part. Here's a star and here's a circled star. Why is this important? Because it's very, I was so confused about this. Like, why is this actually possible that this is parabolas? So this star means this is a stationary point, the energy of a stationary point at the relaxed geometry at potential. Yeah? And this is somehow effective expansion parameters at expansion potential and expansion geometry. So during this potential scan, this potential energy landscape completely transforms. Like basically the transition state moves towards the initial state, and it's like looks very different. Geometries look very different. But nonetheless, the thing remains parabolic effectively. So we said, okay, this is weird. And then my very good student Simeon said, I think I have an idea. And basically he used a generalized second order expansion, which is always correct. Second order expansion in positions. Yeah? To understand how's the relaxation actually happening. And you can do that because we only look at stationary points. Yeah? You can do this in a meaningful way. And in fact, you can solve this analytically. Like, how does the system actually relax when you change the potential. I mean, you can do kind of linear response. And when you do this math, this is here, then you can write down this capacitance. And capacitance is more or less response function, an effective response, second order response function. You can write this down as this quantity C electronic, which is, let's say, the response at constant positions, no relaxation, and then this correction term, which is related to inverse Hessian, and then these mixed response functions. Ground canonical charge change with respect to position, and that's the same thing also. This is just switching around differentiations. This is the same thing as force derivative with respect to potential. So we call this quantity geometric capacitance because it's really just, it appears as if it's a contribution to the capacitance, but what it actually describes is the geometric response, the effect of geometric response to the energy, correct in second order. And so this is kind of, you could think of it as a polarizability. Maybe even more abstract, you could think of solvent reorganization, but I'm not, this I don't want to say. Okay, now this was cool that we could find this because it explains why we see parabolas. I was very surprised that these parabolas exist also for the transition states. And what is the cool thing about this? We have now a model-free second order correct theory for electrochemical energetics and so electrochemical barriers and so symmetry factors. And let's write this down. So electrochemical barriers is energy differences in the ground canonical ensemble between transition and initial state. Well, it should be parabolic. This is the simulation activation energy potential. And you see the diamonds are these constant potential natural elastic band simulations. Yes, they do follow a parabola. So somehow this difference, this quantity is not zero, which surprised me a bit. I'll talk about it later. It's not zero, but it's very interesting because it says that within this very general second order model that should always hold for stationary states in some way, it looks like that the symmetry factor alpha, which is simply the derivative of this energy of the barriers or the slope here, this slope is a function of the potential. So the symmetry factor is a function of the potential in this like most naive level of theory that you can write down. And so we are at this level of theory already beyond the accuracy of a Butler-Volmer equation. That's actually super nice. And what's also nice, we are scaling, or what's interesting rather, we are scaling like a Marcus-Husch parabola model. So, or like from the complexity. And this is interesting, I think, because many experimentalists think or sometimes write in papers, oh, we see the symmetry factor depends on potential. That's why we have here solvent reorganization and Marcus-Husch is right, or this is our Marcus-Husch model. But really this just comes out, I mean, if you do nothing basically, but a parabolic approximation, which is always like meaningful. So I'm a bit, let's say, I would just want to put forward this parabolic behavior or potential dependent symmetry factor doesn't prove we need Marcus-Husch or that solvent reorganization is happening. This is just the most, let's say, simple thing that should happen. About these parameters, so you can determine them with one single minimum energy path simulation. You need to simulate, of course, maybe the potential response, so the capacitance, the Hessians, mixed response functions. Maybe you anyways want to compute Hessians to do some corrections, free energy corrections on this problem. So you get this actually for free. Then you can also, so all the math is here in these papers. So you can, of course, also do constant charge and then apply all these analytical transformations to ground canonical. But the Hessians is important, right? They are different, and of course the transition path is also different in these. But you can all do this analytically, and then, within this second order approximation, and then you can do further approximations. That's maybe the most interesting thing for this quantity here. So we have different approximations here, and one most efficient one is we call it XEGC method. So it's one constant charge natural elastic band at PZZ and nothing else. So no Hessian, no charging, nothing. So we approximate now this Hessian which enters this geometric capacitance. We approximate it simply by the curvature along the reaction path times, of course, you need to look how the reaction path, of course, transforms. But basically, we look at only the curvature here, and then we can recreate these constant potential results completely across the whole potential scale. So here, diamonds are the real computations, and dashed line is this super simple approximation. I think that's interesting because in this approximation, we can resolve why this is not vanishing. And here in this case, it is simply not vanishing from a very fundamental property, from the fact that the Hessian is negative at transition state and positive here. So it's like not even, it's like in this simple model, it's basically not possible that just from the pure geometric properties of these states, that this is a constant. I'm just putting this out there. Okay. And so last words, what are these quantities actually? Now here in the energetics, it's a bit maybe less clear, but I think you can do all of this in the free energy as well, because this is really just pure math in some sense of Legendre transform and so on. I want to highlight that these quantities are thermodynamic response quantities. Yeah. So this Q is not a charge. It's a thermodynamic definition of a charge. It's a global charge. It's an effective charge. It's not a local charge. Certainly, it's not a Bader charge. And it includes, if you would do now here some real simulations with temperature and movement or something, yeah, or do just these corrections that we typically do with harmonic oscillator type, you get entropy effects naturally. I mean, this is not a charge. This is a response function. I want to highlight this and the symmetry factor as well. So there's like, for example, entropy in there. And so this is really very, very, let's say, different. And I think enlightening when you compare this somehow description, which is, I would say, free of any approximation in some sense. Compare this to the traditional viewpoint, like here Husch from 1958, that the symmetry factor is the charge of the ion at the transition state. So I cannot anymore, let's say, link to this description, because if you just think of response functions. Okay. I want to now a bit switch gears, but somehow come back in some sense. I just want to switch gears in some sense because what I talked and what looks so nice, it's all really working out like this. I think we tested this a lot in these simulations, in implicit models, in some quasi-static approximation to interfacial energetics. So these types of simulations. If it works out here, I'm not 100% sure. I would believe in some sense, but I'm not 100% sure. And it is evident that, of course, response is very, very different in a dynamic explicit water simulation. And you see this most clearly at the capacitance when you look at the capacitance of platinum-111. So when you do look at the experiments, you get this massive peak. And this peak has troubled me for, I don't know, like really 8 years or something. Because I started working on these implicit models, and I looked at how I do platinum, and platinum is just very badly done in implicit models. So you get something 15 or 25. You can tune parameters, but it's nearly impossible to make anything realistic for platinum with implicit models. If you now build a typical rather simulation where you have some real atoms also then explicitly treated at this interface, things get worse. I mean, if you say this is the capacitance, what you compute in the implicit model, then things get worse. You're down at 6 or 8 microfarad per square centimeter, so completely gone. No peak, nothing. What now if you do simulations with IMD? And here, the first, let's say, a calming result, yes, if you do DFT, Ab-Initio molecular dynamics with charging with explicit ions, it seems you can somehow reproduce this peak, at least phenomenologically, nearly kind of semi-quantitatively. This is work by the group of Juncheng. On the other hand, I must say, this is not what many DFT people find. Here, I just give an example. This is, in fact, work by Clotilde's group. And this is not a criticism. This is just stating she uses she uses actually a more realistic charging method. So uses anion and cations at the same time, and she cannot reproduce or see this peak, very low capacitance, and many publications that I look at have very low capacitances. And it tells me just that there's, of course, the problem of how good these counter-ion distributions are actually converged. So you might think maybe force fields solve this, but force fields are beyond anything. I mean, force fields, I have never seen a force field calculation that does anything more than 10, and kind of a straight line, basically, and so it's very confusing. Why is, although the water response is not so bad in these force fields, like structurally, but the capacitance is very bad. So the question is, what is going on? And this is kind of, let's say, Langley's PhD project, like what is going on in the system. Kind of difficult, I think, problem, but I think we figured out some important things or contributions or details. So what we did is, we said we don't want to deal with this time scale of the ions. We would like to do to concentrate on water response because it felt, or people already had argued that's probably water response. So we wanted to focus on water response and specifically without ions. So we wanted to have a method where we can bias the system without ions. And so of course the only thing you could do is maybe a field or some homogeneous background charging. That had actually been done already. And so we went and said, okay, let's do maybe a method where we don't charge the metal in that sense, but we build an effective countercharge, homogeneous countercharge in the solution. And we did this by, similar as what actually Mira and Jörg did, or what Mira showed, kind of modifying the pseudopotential, putting small little charges on each hydrogen. And the idea of putting it on each hydrogen was simply that we relax, that this countercharge distribution here in the solvent relaxes on the same time scale as the water density. Yeah.
That's net charge, right?
This is a net charge. This is
net charge.
Excess, yeah. This is an excess charge, positive or negative on here, and then a charge compensation by electrons. Yeah. So yes, these water molecules will be slightly charged. So this is slightly charged, and then we can put electrons. That's the trick. Yeah. So it's a bit fishy, yeah. But you have I don't know, 64, 96 molecules, so you can bring this to kind of rather small levels that you hope, and we checked, of course, that things don't look weird. Yeah. Okay. What do we get? Well, first, some size size. We're looking at consistency with size, and you get exactly what you expect. This is I plot here the bias potential. Yeah. So what is actually potentially biased with? This is pure electrostatics. So we have a charge here and a homogeneous constant countercharge here. So you expect parabolic behavior from the Poisson equation. Everything works out as expected, but it tells you also, okay, we will have a size problem, of course, if we look at potentials here. But because we bias differently for different sizes. But what I want to draw your attention to is this interfacial region here. The slope is kind of independent of the size, and the slope is the field. So somehow the force that the interfacial molecules feel is nearly independent of cell size. So we were hopeful that we can get reproducible results for the interfacial water response, because here the interfacial field matters, the derivative of this quantity. Okay. How does it feel? How does it look now? So we did this test, different cell sizes, then for different charges, plus and minus. And you can see here the water density and here the orientation response. You see this density response that people know. Like you go positive, you see a chemisorption peak coming up, and here the non-chemisorbed water, and you're going negative, that chemisorption basically goes away. So this is known, and we have very consistent results across different scales of our simulation. So that's good, meaning we can just choose one and go on and do more detailed simulations. This we did then, scanning different charges, and then we looked at, is now this interfacial water response, how does that relate to a simulation where you bias with explicit ions? Is there a difference in the interfacial water structure for homogeneous biasing and kind of pointwise local biasing with ions? And it doesn't look really very different, I would say. You can see here for some significant bias, the water response, again, this is the chemisorption peak, and this is the then peak where nothing is chemisorbed on the water, on the surface. And you see we reproduce these dashed lines, which are at identical surface charge, nominal surface charge. These are work again by the Junjang group. We can reproduce this, I think, very nicely. For example, the coverage with chemisorbed water as a function of charge, we can reproduce this in a very nice way. And so we were quite confident that our interfacial water structure that has no ions is kind of really the let's say the interfacial response. This is a realistic pure water response. Exactly, and it's kind of very robust and very similar to the real system with explicit ions. Now, what can we do with this? Well, we said now we want to try to see if this already explains that peak, if this explains everything, this interfacial water. And there were some hints by this publication that it's mainly interfacial water that does the thing. I mean, here was the idea, it's only chemisorbing waters. We were a bit less daring. We were just saying or testing only interfacial water to not have to make a discrimination between chemisorbed and not, and then, sometimes it's not clear maybe. Okay, so how do we do this? And it's kind of a test. I think it's an intrinsic test for implicit models, because what we did is we put now the response from the all-explicit simulation, the structure of the water from these all-explicit simulations at bias, we put them into an implicit solvent model, such a setup, and then we analyze, let's say, the potential or the work function in this implicit model setup. So basically we test what would the potential be, yeah? If we had true interfacial water response sandwiched inside an implicit solvent model approach. And then it's easy to kind of think what would the capacitance be, where the capacitance can then be written as a sum of two inverse capacitances. One is the implicit model capacitance, and that is and here they call it the negative component of the Helmholtz capacitance in some sense. Yeah? Negative capacitance, this is from this response. The response is always negative. Yeah? Let's say this water reorientation. So we wanted to test, is this approximation, or like non-self-consistent, working out to reproduce this? And the result is really, too good. And it's really it's not realistic to believe that it's so good. But it's, I think, a strong indication that things, let's say, work like this. The true origin behind that peak is only, or dominated strongly by only this interfacial water response. And it also tells me that I think these implicit models are not too bad. Yeah? If we had the true interfacial water response combined with implicit model response, things don't look actually so bad. Maybe a short note here. We have here a peak. A second peak, we plotted here a second peak. We called it C orientation and implicit. What we did here is we said, what is actually the influence of the metal? So we took now this interfacial water, we put it in vacuum, we look at the potential drop in vacuum across the structure of this interfacial water. So this is kind of, in some sense, I think this is the equivalent of what maybe in a non-polarizable force field would do. So this is kind of dipole orientations. And we get this result, or a polarizable force field rather. So this is this result, then the blue curve, and it says, well, already just the orientation response and no, let's say, chemistry with platinum gives us already a peak. But it also tells us that to really understand this peak, you need also this chemistry with platinum, this kind of charge transfer that happens when you put water on platinum, and Mira has actually talked about this charge transfer that exactly is exactly this quantity that makes this peak higher in our, let's say, analysis of the problem. Okay, a few last words. How many minutes do I have? 5. Okay.
Not quite. 5 minutes.
Okay. Thank you. It's fine. I will be a bit rushing because I still wanted to say 2 things to this machine potential. But let me first finish this. So one important thing I also want to highlight, and I make it very short, is that the significant problem with force fields. So we did here in this publication a lot of analysis, let's say, of interfacial potential drops now, in particular due to bias charge. Yeah, where do the electrons actually go in space? And what I'm saying is like the excess electrons. And what I want to say is, so just very briefly, the force fields completely fail. I showed it before because they put the electrons at the wrong position in space. Yeah, because they put it here. That's why capacitances are super low. A vacuum simulation already kind of has this known, let's say, smearing spillover into the vacuum. Yeah? This already helps in terms of magnitude of a capacitance, but it's still not working out logically if you think about the order of magnitude of these capacitances that you can read off simulations. The only way that you can really rationalize, in my opinion, what's happening in the experiment is that you have a kind of double peak. Or this is what you see. When you put interfacial water there, true interfacial water, and you bias the system, you see that the excess charge goes here into this region where you have the excess charge in vacuum, but it also goes in a significant amount into the interfacial water region. Yeah? So beyond this chemisorption. Yeah? And I want to also say, we called it here charge spillover, and you can imagine, of course, this is a total different electrostatic problem now, right? This is not a plate capacitor. This is somehow charge counter ions here and charge here. Yeah? So this is a very different problem than this is a very different setup of charge distributions as compared to the typical plate capacitor logic of a Helmholtz model. Thank you. Yeah, so this is what I wanted to say here. Sorry, I got now confused. Yeah, that's I think all I wanted to say here. Well, in summary, it looks like, and so I think, yeah, this is a very important thing. So So we need DFT. And so in summary, it looks a bit like maybe if we could get true interfacial water response in an implicit, more sandwiched in an implicit solvent model, maybe we would be very good in terms of realism to experiment, relative to experiments. But if you have just one water layer, you will just, of course, the forces are so different that it wouldn't work. So you kind of want to go definitely to bigger systems. And this is kind of something we wanted to do. And I think we are kind of towards this goal by creating basically a machine learned potential built basically with the use also of implicit solvent models. We called it RAZOR, the response analysis in Z orientation. And this was really a very nice collaboration with Nicolas Hörmann and Nicolas Mazzari. My student Nicolas Bergmann did a kind of exchange, and within a few weeks we had something very interesting running. I'll tell you now the idea. I have still 5 minutes, I hope. So the idea was we want to learn the constant charge potential energy surface, so this quantity. And then the idea was, okay, maybe we can do it perturbatively. Yeah? We have done all these perturbations. Maybe let's try first if we can do it approximately. Yeah? So let's try this approximate version. Okay, so we expand total energy around potential of zero charge conditions. Then this first response property is the work function. Then we do the same for the forces. Yeah? We get forces at let's say, neutral forces, and then forces at charge conditions, change in forces with charge. This is the same as work function change with respect to positions. And now you see this is the quantity that every machine learning model, let's say, needs to or learns, yeah? And it decomposes this total energy basically into individual atom contributions. Now this quantity, and it looks like maybe we could learn this, yeah? But a kind of small problem, this is intensive, so it doesn't really fit the typical architecture. And so we said, okay, maybe we can just do some trick and map things around. So we said, now let's map this onto an extensive quantity, namely the interfacial polarization. It's just multiplication by epsilon 0 and A. This is just formally, right? So we transform these quantities into extensive quantities, yeah, like Z-projected polarizations, basically. And then we can also, of course, look at this position derivative, which is like the position derivative of the Z-projected polarization, which is the force change with respect to Q, which, and here's really the interesting thing, nominally, this thing is the same thing as a projected Born effective charge tensor. So when I saw this and realized this, I was like, that is really interesting, because maybe we're going towards, really stabilize, like going towards robust thinking, about thinking much more robustly electrochemistry, because, let's say this is what physicists understand and know a lot about. Okay, so to make it short, we use these quantities for training, and we can train them with in this way. Or let's say I show you how we built this machine learned potential. So we have a standard machine learned potential, standard, in a sense, DFT calculations at vanishing charge, energy, forces. We learn this. Then we do now DFT calculations at different charges. We determine these numerical derivatives. In essence, these Born effective charges. Here you can see these are these projected Born effective charge tensor elements that we plot here. And then this is maybe one thing that was not trivial, and this was a lot also, I admit this was an idea of Nicolas Hörmann, that we learn not a scalar here, but we learn a projected equivariant kind of vector property. And if you do this, you can implement this very easily. Things kind of work. Yeah? You can recreate this response and build a machine learned potential that is kind of first order correct. Yeah? And the nice thing about this logic is we can go to higher orders. It's very modular. We can use different architectures here. You can use a pre-trained foundational model that you trust, and you just learn the delta, the energy delta and force delta. Yeah. So we just actually got just accepted, and yesterday I got the proof, but I didn't have time to look at it. So first test, okay, 2 more minutes. First test, and then I'm really done. First test, we combine, and here you can see it's very modular. We use mace and neck whip for the razor, and we simulate now here OH on copper. And what we observe is if we charge, we have OH on the bridge at negative charge, and then booms, suddenly a kind of phase transition, OH moving into the hollow. And here in green, you see like that you really suddenly jump in the hollow positions by biasing the system to positive surface charge. Now you can, of course, say, okay, how do we get energies from this? And the nice thing about the MD is always, there's ways to go to free energies. And so the way we do it here is we do thermodynamic integration. So you have to integrate the observed, let's say, work function in the Q ensemble and integrate over Q. This we have from our MD and from the prediction of Razor. This is, let's say, something we add in because we didn't learn capacitances, so I can talk about this later. But then with this method, we can get really free energies as a function of charge, and you get here these blue curve, smooth curve, that tells you how the interfacial charge or the adsorption energy, let's say, how that changes with respect to charge. Now, as a test, this is more like a test, does that make sense, what we get here? And I think it very much does make sense because we can test this phase transition, if you wish, or the switching of the adsorption side by some Ab-Initio thermodynamics. And so you just put two hydroxides at these adsorption sides, you look at their potential dependence, determine the energy in the typical Ab-Initio thermodynamics way, and you get these red curves, and you see exactly they follow very nicely this MD free energy, and they also explain equally why or that this switch of the adsorption side should happen. So we're very trusting right now, or for the moment, we trust very much that this MD really works. Of course, to go to ground canonical properties, we Legendre transform, but this is just a detail. This is all the information is there to Legendre transform. And so take-home message. Well, I think it is really my opinion that somehow the field is moving towards a kind of modern theory of electrochemistry. So where we only use quantities that we can compute and that are well defined. Looking at energies and response functions, I think is a very nice thing. This is what really everybody else, or what many people do. And I just put here the general idea, I think, out. And so I wrote this a bit up in this publication. I'm not sure if it's very... I tried my best to make the broadest overview of what's happening at the moment in this field. And with this, I'd like to thank, of course, my coworkers, my boss, Karsten, and of course, my group, and especially the people that did the work. This is Simeon, who did this a lot, these mathematical analysis of the relation between ensembles, Nicolas Bergmann, who developed Razor, and Lang Li, who worked on the Patimo 1.1. She's also here, and I just want to highlight that Barbara, also a PhD student, she's also... where is she? Can't see. There. Yeah. She's also here. I didn't have time to talk about her work. Thanks a lot.